What if history books told a different story? A story not just of kings and battles, but of the quiet revolutions waged in laboratories, observatories, and at the very frontiers of human knowledge. For too long, the narrative of scientific progress has been woefully incomplete, often sidelining or entirely omitting the monumental contributions of women. This isn't just a matter of historical accuracy. It's a profound loss for science itself, a silencing of diverse perspectives that could have accelerated our understanding of the universe and our place within it. When we fail to recognize half of humanity's intellectual power, we inadvertently dim the very light of discovery, limiting the scope of our questions and the breadth of our solutions. The persistent underrepresentation of women in scientific fields, both historically and, in some areas, even today, has created a skewed perception of who can be a scientist and what scientific genius looks like. Imagine the breakthroughs delayed, the insights missed, because a brilliant mind was denied access, resources, or simply the recognition she deserved. This systemic oversight has not only impacted individual careers, but has also subtly shaped the direction of scientific inquiry, potentially overlooking avenues of research that might have been prioritized by a more inclusive community. The societal impact is equally significant, as it deprives young girls and women of visible role models, perpetuating a cycle of exclusion that we are only now beginning to earnestly address. Have you ever heard of the woman who discovered the first antibiotic? Or the scientist who mapped the human genome? These women changed the world, but their stories are rarely told. Let's dive into the untold stories of women in science and uncover the brilliant minds behind some of history's most significant discoveries. We're going on a journey to reclaim these narratives, to shine a cosmic-sized spotlight on these hidden heroes, and to understand not just what they discovered, but the often challenging paths they navigated to bring their truths to light. Prepare to be astonished, inspired, and perhaps a little outraged as we rewrite the guest list for the pantheon of scientific greats. When we speak of pioneers, of those who fundamentally altered our perception of the universe, the name Marie Curie rightly resonates with a unique luminescence. Born Maria Skłodowska in Poland, a land then under oppressive rule, her early life was a testament to an unyielding thirst for knowledge against formidable odds. She pursued her education in Paris, often subsisting on little more than bread and tea, driven by an insatiable curiosity about the physical world. It was here, in the vibrant intellectual crucible of the Sorbonne, that she would meet Pierre Curie, a partnership that would become legendary not just in science but in life. Together they embarked on an exploration into the mysterious rays emitted by uranium, a phenomenon recently discovered by Henri Becquerel. Little did they know they were standing on the precipice of a new era of physics. Curie's work wasn't just about observing, it was about rigorous, painstaking experimentation. She coined the term radioactivity to describe this strange energy, and her meticulous investigations led her to theorize that this property was not the result of molecular interaction, but an intrinsic characteristic of the atom itself. This was a revolutionary idea, challenging the long-held belief that atoms were indivisible and immutable. To prove her hypothesis, she and Pierre undertook the Herculean task of isolating the sources of this intense radiation from tons of pitch-blende ore, working in a dilapidated shed with primitive equipment. It was a labor of love and sheer grit, a testament to their dedication to uncovering the universe's secrets, no matter the personal cost or the physical toll. The discovery of two new elements, polonium, named in honor of her native Poland, and radium, was a monumental achievement that earned Marie Curie her first Nobel Prize in Physics in 1903, shared with Pierre and Becquerel. She became the first woman to receive this honor. But her journey didn't stop there. After Pierre's tragic death, she continued her research with even greater resolve, eventually isolating radium in its pure metallic state. This work earned her a second Nobel Prize in 1911, this time in chemistry, making her the only person to this day to win Nobel Prizes in two different scientific fields. Her legacy extends far beyond these accolades. She pioneered the use of mobile X-ray units during World War I, saving countless lives, and fundamentally changed our understanding of matter and energy. In the grand cosmic theatre of scientific discovery, some players take center stage while others, equally brilliant, remain in the shadows, their contributions obscured until history, with its slow but persistent gaze, brings them into the light. Such is the story of Rosalind Franklin, a meticulous and exceptionally skilled X-ray crystallographer whose work was absolutely pivotal to one of the 20th century's most significant breakthroughs, the elucidation of the structure of DNA. Her journey into the heart of the molecule of life was marked by intellectual rigor, but also by the pervasive sexism of the scientific institutions of her time. Imagine the focus, the precision required to aim X-rays at infinitesimally small crystals of DNA, and then from the patterns of scattered light, deduce the intricate architecture within. Franklin's expertise in X-ray diffraction techniques was unparalleled. At King's College London, she produced remarkably clear and informative images of DNA fibers, most famously, Photo 51. This single image, obtained after painstaking hours of work, was a lightning bolt of clarity. It revealed to the trained eye the unmistakable helical structure of DNA, its dimensions and the regular spacing of its components. It was, quite simply, the crucial piece of experimental evidence that unlocked the puzzle. Yet the environment at King's College was not always collegial for women. She faced isolation and a lack of respect from some of her male colleagues, a stark contrast to the collaborative spirit she had experienced in her previous post in Paris. The story of how Photo 51, without Franklin's full knowledge or permission initially, made its way to James Watson and Francis Crick is a complex and often debated chapter in the history of science. What is undeniable is that this image provided them with the critical insights needed to build their correct model of the double helix. While Watson, Crick and Maurice Wilkins, Franklin's colleague at King's, received the Nobel Prize in 1962 for this discovery, Franklin had tragically died of ovarian cancer 4 years earlier, at the young age of 37, and Nobel Prizes are not awarded posthumously. Her contribution, though, is now widely recognized as fundamental. She was an architect of our understanding of life itself, her keen eye revealing the elegant blueprint encoded in our very cells. Let's rewind the cosmic clock back to the 19th century, an era of steam engines and burgeoning industrial might, but also a time when the seeds of the digital age were being sown by a most remarkable mind, Augusta Ada King, Countess of Lovelace, or as we better know her, Ada Lovelace. Daughter of the famed poet Lord Byron, Ada was steered towards mathematics and logic by her mother. Perhaps as an antidote to what she perceived as Byronic madness, little did she know, this path would lead Ada to become a visionary who saw far beyond the mere calculating machines of her time, envisioning a future where machines could create, not just compute. Her intellect was a bridge between the poetic and the analytic. A rare and powerful combination, Lovelace's enduring fame stems from her collaboration with Charles Babbage, the inventor of the analytical engine, a theoretical, general-purpose mechanical computer that was, alas, never fully built in their lifetimes. While translating an Italian mathematician's paper on Babbage's machine, Ada didn't just translate, she expanded, she annotated, she illuminated. Her notes, appended to the translation, were 3 times longer than the original article and contained what many consider to be the first computer program, an algorithm designed to be carried out by a machine to calculate Bernoulli numbers. This wasn't just a sequence of operations, it was a demonstration of how the analytical engine could be instructed to perform complex tasks. But Ada's vision soared even higher. She speculated that the engine might act upon other things besides number run. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. She foresaw a world where machines could be partners in creative and intellectual endeavors. A concept that was profoundly ahead of its time. She understood the fundamental distinction between the hardware, the engine itself, and the software, the instructions, the programs. While Babbage focused on the machine's capacity for numerical calculation, Lovelace perceived its potential as a universal manipulator of symbols, a truly profound insight that resonates deeply with our modern digital age. She was, in essence, a prophet of the computer age, the Enchantress of numbers. Imagine trying to determine the precise 3-dimensional arrangement of atoms in a complex biological molecule. a molecule so tiny it's invisible to the most powerful light microscopes. This was the challenge embraced by Dorothy Hodgkin, a chemist whose pioneering work in X-ray crystallography unveiled the structures of some of life's most vital substances, transforming our understanding of biochemistry and medicine. Her journey began with a childhood fascination with crystals, a passion that she pursued with unwavering dedication despite societal expectations and the physical challenges of severe rheumatoid arthritis, which afflicted her from a young age. She didn't just look at crystals, she sought to understand their innermost architecture. Hodgkin's method, X-ray crystallography, involves shining X-rays through a crystallized form of a molecule. As the X-rays pass through, they are diffracted by the atoms in the crystal, creating a complex pattern of spots on a photographic plate. Deciphering these patterns is an incredibly intricate mathematical puzzle, requiring immense patience, intellectual rigor, and often years of painstaking calculations, initially done by hand or with rudimentary mechanical aids. Hodgkin possessed an extraordinary ability to visualize these three-dimensional structures from the abstract data, a kind of molecular artistry guided by the strict laws of physics and chemistry. She was, in a very real sense, sculpting molecules with light and shadow. Her list of achievements is staggering. In 1945, after years of meticulous work, she determined the structure of penicillin, a discovery crucial for its synthesis and widespread use as an antibiotic, saving countless lives during and after World War II. Then, in 1956, she unveiled the even more complex structure of vitamin B12, a molecule vital for preventing pernicious anemia. For this groundbreaking work, Dorothy Hodgkin was awarded the Nobel Prize in Chemistry in 1964, becoming the third woman to win this prize in chemistry following Marie Curie and Irene Joliot-Curie. Later, in 1969, she and her team solved the structure of insulin, a hormone critical for understanding and treating diabetes. Her work laid fundamental groundwork for drug design and molecular biology, a true titan of structural chemistry. Sometimes the universe reveals its most profound secrets through the most unassuming of subjects. For Barbara McClintock, that subject was maize corn. But this was no ordinary study of crops. McClintock's decades-long, deeply intuitive and rigorously experimental work with corn plants led to one of the most revolutionary discoveries in genetics, the concept of jumping genes or transposable elements. In an era when the genome was largely considered a static, orderly library of information, McClintock's findings suggested a far more dynamic and adaptable genetic landscape. Her insights were so far ahead of their time that they were met with skepticism, even confusion, by many of her peers. McClintock spent countless hours in the cornfields of Cold Spring Harbor Laboratory, meticulously observing the inheritance of kernel colors and patterns. She noticed that genetic mutations didn't always behave predictably. Some genes seemed to turn on and off, or even change their position on the chromosome. This was radical. She hypothesized that there were mobile genetic elements, controlling elements as she called them, that could move around the genome, influencing the activity of other genes. This wasn't just a minor tweak to genetic theory. It was a paradigm shift, suggesting that the genome itself could actively reorganize and regulate itself in response to developmental cues or environmental stress. For years, McClintock's work was largely underappreciated, its profound implications not fully grasped by the wider scientific community, which was then heavily focused on the molecular biology of simpler organisms like bacteria and viruses. But she persevered, driven by her deep connection with her research material and an unshakable confidence in her observations. It wasn't until the late 1960s and 1970s when similar mobile genetic elements were discovered in bacteria and other organisms using new molecular techniques that the scientific world finally caught up to McClintock's visionary insights. In 1983, more than 3 decades after her initial discoveries, Barbara McClintock was awarded the Nobel Prize in Physiology or Medicine, a long overdue recognition for a scientist whose brilliant mind saw the intricate dance of genes long before others could even imagine the music. The stories we've explored today of Marie Curie, Rosalind Franklin, Ada Lovelace, Dorothy Hodgkin, and Barbara McClintock are more than just fascinating historical accounts. They are powerful reminders of the indomitable human spirit of inquiry, of the brilliance that can flourish even in the face of adversity and systemic barriers. These women, and countless others whose names we may not yet know, fundamentally reshaped our understanding of the universe, from the subatomic realm to the code of life itself, from the very nature of computation to the molecular basis of health and disease. Their legacies are not just in their discoveries, but in the paths they forged for future generations of scientists of all genders. Recognizing these hidden heroes is crucial. It reclaims a more accurate and complete history of science, demonstrating that genius knows no gender. It provides powerful role models for young people, especially girls and young women, inspiring them to pursue their own curiosity and to contribute their unique perspectives to the ongoing quest for knowledge. The universe is vast and full of mysteries, and we need every brilliant mind, every diverse viewpoint to help us unravel them. By celebrating these pioneers, we enrich our present understanding and empower a more inclusive and therefore a more innovative future for scientific discovery. Let their stories ignite your own curiosity and passion. The cosmos of knowledge is ever expanding, and there are always new stars of discovery to find. We've only scratched the surface of the contributions made by remarkable women throughout the history of science. Who are the hidden heroes that inspire you? Share their stories, seek out others, and let's continue to illuminate the often overlooked constellations of human achievement. For videos like this, please follow and subscribe. See you on our next video. See.